Let's take a look at one more example. We again have a matrix A. We want to determine if it's diagonalizable, and if so, find the invertible matrix P, the diagonal matrix D, that will make that diagonalization work. Okay. Again, a matrix is only diagonalizable if it has, if matrix P is invertible. So that means that our set of eigenvectors, we have to have a linearly independent set of eigenvectors equal to the number of rows and the number of columns of matrix A. So in this case, again, we're having a 3 by 3 matrix, so we need 3 linearly independent eigenvectors. All right. So we're going to use the calculator to find those for us. We could do it by hand, but it is a lot of work to find those eigenvalues and eigenvectors. So let's let the calculator do the hard work for us. So I'm going to input the matrix. First row is 360, second row is 520, and last row is 0, 0, -3. And we want to find the eigenvectors of A and their associated eigenvalues. Okay. Okay, so we have two distinct eigenvalues, -3 and 8. Again, we have some multiplicity here, right? -3 occurs in the characteristic equation twice. There are two factors in the characteristic equation that have that root. And one factor in the characteristic equation with that have root 8. Okay, but how many eigenvectors do we have? In this case, -3 has 2 associated eigenvectors. So its eigenspace has dimension 2. Okay, 8 has 1 associated eigenvector, but put that together, that's 3 eigenvectors. That's what we need, which means that A is diagonalizable. Because I have 3 linearly independent eigenvectors. All right, and we can easily find matrix D and matrix P now. So matrix D is going to be equal to the diagonal matrix where the diagonal entries are the eigenvalues, right? Now I have 2 eigenvalues, but I should have 3 entries along the main diagonal. So the trick here is if you have an eigenvalue with multiple linearly independent eigenvectors, like we do here. -3 is an eigenvalue with 2 eigenvectors. That -3 needs to occur twice in your diagonal entries. Okay, once for each eigenvalue. So I'm going to have -3 occur twice down that main diagonal, and then 8 once. And then matrix P, the columns of matrix P are going to be the eigenvectors. So my first 2 columns should be the eigenvectors associated with -3. And I've got 2 eigenvectors associated with -3. I need both of them in there. It doesn't matter which order they're in. Okay, so I could do -1, 1, 0 first, or I could have 0, 0, 1 first. Doesn't matter. Okay, I'll just stay in the order that the calculator gives us. So column 1 will be -1, 1, 0. Column 2 will be 0, 0, 1. And then finally, the last column should be the eigenvector associated with 8. That's 6/5, 1, 0. So 6/5, 1, 0. I have my answer. Okay, that gives me an invertible matrix P and a diagonal matrix D that make the similarity between A and D work. Matrix A is similar to this diagonal matrix, and therefore it is diagonalizable. All right. Now, one final thing. This is a perfectly fine answer. But if it were me, I would just tidy up this matrix P. I see I've got a fraction in there, and since any scalar multiple of an eigenvector is still an eigenvector, I can multiply this eigenvector by 5 and get rid of the fraction. So if I multiply the eigenvector by 5, I would get 6/5 times 5 is 6, 1 times 5 is 5, and then 0 times 5 stays 0. And that works too, and I think it's just a little bit prettier to look at, a little bit easier to work with.